Okay, so I guess one of the nice things about organizing a conference, you don't have to speak. But these guys. So, welcome. Unfortunately, I do have to say something. I was going to give. I keep changing what I'm going to talk about. So let me talk about the Archimedean theory of the affine sieve, since that'll dovetail, I think, nicely with Alireza's lecture. So this is the Archimedean theory. And actually, we haven't had a discussion of sieve methods at all yet. We've been talking about what they do, but Henrik's here, so let me begin at the beginning. So, okay, let's say we try to sieve just for primes. So here's example 1. You always have a sifting set, and you try to throw away the non-primes from your sifting set. So let me take my sifting set S, just be the integers, or the positive, the natural numbers. Okay? And what's the Legendre sieve? Well, how many primes are there up to x? It's just the number of integers there are up to x. So let me give a definition. S of x, let's see, can you see all the way over there? S of x is S intersect the first x integers. So how many primes are there? Well, it's just the number of elements in S of x. That's the crudest estimate you have, but then you want to throw away the evens. So you throw away S of x intersect twice z. And then you also need to throw away the multiples of 3. So you throw away the number of elements in 3z. But of course, you've thrown away the multiples of 6 twice. Everybody knows this inclusion exclusion argument. 6z, and so on. And once you do this, so the whole idea in Eratosthenes' sieve is that you only need to do this process for primes going up to root x. Because if a number has no prime factors, if you've thrown away all the prime factors at most x, then the number is prime. That's the key insight of Eratosthenes. And of course, we've thrown away these primes. So let's just estimate rather trivially that there are no more than root x primes up to x that have been discarded. Okay? And how would you get at this estimate? Well, how many numbers? Remember, S is integers. So how many integers are there up to x? Well, there's x. How many even integers up to x? Well, x over 2. And how many? So the number, this will be kind of the key point, the number of integers in some progression up to x is just the total number divided by the modulus. And Peter hasn't screamed it yet, but he screamed it yesterday, plus 1. Right? There's a remainder term. Let me call this plus remainder term. And note that we have this bound on the remainder term. Okay. Now, this remainder term will be insignificant, right? It's just of size 1 at most. So let's just ignore it. So what do we get here for the main term? Okay, so the size of the first thing is just the number of S of x. For the second thing, so that contributes a 1. Then we get a minus a half, minus a third, plus a 6, and so on, up to primes of size root x. And of course, we can write that as, so here's S of x. We know how many numbers are up to x. There are x of them. And what's left is a sum over all of the divisors of the product of the first root. Each one comes with a 1 over q and some sign, and that sign is exactly the Mobius function. Okay? And this thing is, it's easy to see that this is completely multiplicative. So it multiplies as a product over all primes up to root x of 1 plus Mobius of p over p. So if you're not used to factoring things like this, let me convince you. As you take this product, any prime you either include or you don't include. which means in each prime you either take, when you FOIL all this out, you either take the 1, which means you don't include the prime, or you take this factor, which contributes this, and that ranges over all the divisors. Okay? Now, Mobius of a prime is -1. Yeah, the grad students, good. This is supposed to be a workshop. Okay, and there's this old theorem of Mertens that if you take the product of the primes up to z, 1 over p inverse, so this is zeta. Of course, zeta at 1 diverges, so if you stop at some finite number of primes, that diverges to infinity at the rate e to the gamma log z, where gamma is the Euler constant. Okay, so now I'm going to put in root x. And in this product, I don't have an inverse. And so what do I get if I continue this computation? So what I get is a number of primes up to x, ignoring errors, is x. I'm missing the x. Grad students, the x was supposed to make its way over, times this thing. And this thing is 1 over this. I don't have an inverse here. So 1 over this is 2 e to the minus gamma, 1 over log x. So that's the prime number theorem. The number of primes up to x is x over log x times this constant, which is actually 1.12 something. It's pretty close to 1. Okay, that's obviously wrong. And what went wrong? Well, we didn't keep track of the remainders. So what this proves is if you don't keep track of the remainders, you're in big trouble because they have to contribute at least as much as the main term because you got the wrong main term when you sieved. Okay, that's the first caveat. Now, if we actually go to analyze these remainders, how many times are we adding these remainders? We get one remainder for each divisor of the product of all primes up to root x. This is exponentially large in x, whereas the main term is polynomial in x, so size x. Okay, so that not only are the remainder terms completely blowing up, but they're blowing up much, much faster. Okay, so you can't do this. This is the naive Legendre sieve. And what you should do, so what Brunn figured out is a very, this is 1919, a very complicated method which allows you to recover something by a very careful analysis of where you should truncate, where you shouldn't truncate, a lower bound, upper bound sieve. Everyone should buy all of Henrik's books and learn about these things inside out. But here's the upshot. So here's what you should get out of this. It's the following. It's the notion of a level of distribution. So that's the key ingredient in what I'll speak about. So if the sum, if these remainder terms, when you add them up to some number called q, this is called the level. This is the level of distribution of your sequence. Okay? So when you add up these remainders and you stop where you truncate how large a remainder you're going to add up, if this is, don't look, I'll just write little o. You need more. You need lots of powers of logs for applications. But let's say it's little o of the number of elements in the sieving set itself. Okay, so that's what I'll call a level of distribution. And, well, what do you mean little o? If I just take q equals 1, then I want to take this level as large as possible that I can still prove a statement of this form. Okay, so in our case, how large can we take q? The main term is of size x. The remainders are all of size 1. So how big is capital Q? Anything little o of x, like x to the 1 minus epsilon. Right? So in our example, so this is for example 1, the level of distribution, let's say, is x to the 1 minus epsilon. So if you can prove a statement like this with q as large as some power of x, x is the cutoff parameter. We're looking only at numbers of size at most x. alpha positive, bless you, then you can sieve. Okay, so in this case, and this alpha is called the exponent of distribution. So what I want to explain is how the spectral gap gives a positive exponent of distribution, and that's why the affine sieve works. Okay, in a very kind of baby way. And what does it mean you can sieve? Well, you can do two things, typically. You can get upper bounds for the number of primes in your set of the correct order of magnitude. Okay, so in this case, you'll get an upper bound x over log x. And two, you'll get a lower bound. You'd love to get a lower bound on the number of primes of the correct order of magnitude. What you'll get is a lower bound on the number of r almost primes. So these are numbers with at most r prime factors. In fact, they're numbers all of whose divisors, prime divisors, are of size at least x to the 1 over r, which is a slight generalization of Eratosthenes' idea. Okay, where r, what is r? Well, it depends on alpha. It depends on a lot of things, but the most important thing that it depends on is if you have a level of distribution which is at least some power of your main growing parameter, in other words, if you have a positive exponent of distribution, then you can produce r almost primes with r finite. And if you want to think very heuristically, take r to be like 1 over alpha. And if you do that, well, 1 over 1 minus epsilon is a little bit more than 1, and so you can produce 2 almost primes in the integers by applying a Bruin sieve. You have to do a weighted sieve. It's more complicated. I'm doing the very, okay, don't look at me. You know the truth, and I'm lying a lot, so don't worry about it. This is roughly what's going on. All right. Any questions so far? Okay, so let's see let's see a few more examples. So here's example 2. By the way, so in Alireza's talk, we looked at the Mersenne numbers and looked for Mersenne primes. So Mersenne numbers are 2 to the x minus 1. This is our sifting set S. So the set of all of these is our set S. And how many numbers are there in S of size x? Let me write this 2 to the n minus 1. How many numbers of the form 2 to the n minus 1 are there at most x? Log x, right? Because log's bounded, right? The point is, if you want to study these numbers, why doesn't the sieve work? First of all, it shouldn't work because the statements that you would want to prove are false. Never mind. Why doesn't it work? Well, what you would like to do is understand the distribution of these numbers in progressions with progressions as large as x to a power, but the number of points is log x. So you can't possibly save a power or many powers of log in the sieve. Okay, there are many other reasons that it can't work and it shouldn't work. Let's take our set to be, so new example, new sifting set. It's the primes themselves, maybe shifted by 2. Let's try to prove the twin prime conjecture. Okay, so we want to know how many primes, shifted primes, there are up to x in a progression in 0 mod q. And there's a beautiful theorem of Bombieri-Vinogradov which would follow from the generalized Riemann hypothesis, but doesn't use it. It's a beautiful unconditional theorem. So how many primes will you find? Well, assuming q is odd, what should you find? You should find phi of q progressions. The number of primes that can possibly be in this set will be equally distributed in these residues. Okay? So that's the remainder term that we want to bound. And if you sum this up to capital Q, you can bound this by what it should be, let's say x to the 1 minus epsilon, because the total number of primes crudely is of size at most x, with this level of distribution as large as x to the 1/2. So the content of the Bombieri-Vinogradov theorem is that the shifted primes, it's more general than this, I'm doing this particular case. The shifted primes have exponent distribution 1/2. So there are infinitely many primes, p, so that p plus 2 is a product of at most 3 primes. And if you want to do Chen's theorem, you have to work quite a lot more. I know I'm cheating. Yes? X to a large power of log. Yes, of course. But let me. Here I had little o, which is even worse. But if I make q much smaller. No, you're right. Okay. Okay. So that's another example. And by the way, so what would we like to know? So there's a conjecture, the Elliott-Halberstam conjecture. Says that 1/2 should be 1. And now it's very important that you have minus epsilon here, not logs. Okay. So these are two examples. We haven't seen the affine sieve yet. This is just the classical sieve as a warm-up for the affine sieve. Any questions so far? Now we're really getting into the Archimedean theory and the kind of the grits of how the sieve works. This is individual Riemann. This? No, I mean the Vinogradov. Yes? Yes. So if it's a corollary of that. It's an easy corollary of that, where you take the error, each error is at worst root x. So that's what, so the Riemann hypothesis lets you count primes in progressions very accurately. And how many should there be? It's what you expect, and the error term is root x, independent of q. So you're adding root x to itself q times. You can only add root x's to themselves and still be at most x. That's why this follows from the Riemann hypothesis. And this is going far beyond that there should be extra cancellation in numbers that we have no idea how to get at. And I guess I should say, going into this range was one of the key ingredients, at least for smooth Q in Yitang Zhang's work on bounded gaps between primes. Okay, so now let's see something that's starting to look like an affine sieve. So here's example 3. Again, very classical. Let's look at Pythagorean triples. So Elena, the first thing was not the Apollonian, the first affine sieve example. The Apollonian was the one that once Ligarius told Sarnek about. That's what everyone started playing with. The thin Pythagorean, I'm getting there in a second. So there was a test case before the Apollonian, which was the Pythagorean triples. So I'll add the word thin in a second. So let's just look at what happens for Pythagorean triples. And this will also explain the role of why is Zariski density for, if you're comfortable with Zariski density, then you've been happy all along. If you're not comfortable, hopefully this can help you think about it somehow. So what are Pythagorean triples? I have my quadratic form f, x squared plus y squared minus z squared. Okay, it's defined over Q. And I look at the cone, f equals 0. So this is literally a cone. And what are Pythagorean triples? They're just the integer points. So this, when I draw this, I mean the real points of the cone. And now I want to take the integer points. That's the Pythagorean triples. And I guess I want to take the primitive ones so that the GCD is 1, right? You can always, if they have some GCD, you can throw them out. And there's an orbit there's an action on this cone by the stabilizer group, by a group gamma, where gamma is the orthogonal group, or special orthogonal group, let's say, with integer entries, although in the definition of we'll just define it as a variety. What is it? It's the set of matrices, group of matrices in SL3. So let me define SOF. It's matrices in SL3, but now I'll stick in Z's everywhere, with the property that they don't change. So if you take some vector v, x, y, z, you can compute f of it, or you can act on this vector by m, and that shouldn't change the value of f for all v. And it's easy to see that that's the same as, so this quadratic form f has a gram form, 1, 1, minus 1. And so how do I compute f of v? I just multiply by v on the right and by the transpose on the left. And so this is equivalent to m 1, 1, minus 1 m transpose, because that's what happens when I put a v on both sides, is the same as 1, 1, minus 1. Okay. And now it's clear why this is an algebraic group, if it wasn't already. This is a equation on m, just some polynomial. And this is a quadratic equation in the entries of m. Okay, so it's some algebraic condition. And now I want to take the entries to be in Z to get my discrete group gamma. And this discrete group acts on the cone. There are lots of points. This group is, as Peter was saying, you can realize this through the spin morphism as just a copy of SL2Z essentially. And you can take some function. So let's take an orbit. Let me take here's my favorite Pythagorean triple, maybe yours too, and take the orbit of V naught under gamma. Actually, because gamma is the full SOF, depending on how you define it, there's one orbit, or at least the most finite number of orbits. And so there are two inputs, as Alireza discussed this morning, to the affine sieve. First, you need your set of points, which is your group, or if you like, your orbit. And then you need some function. So let me take an explicit function, f of x, y, z. Let's take the area. Okay, 1/2 xy. Now, actually, it's easy to see that all of the areas are divisible by 6. And so I should divide out by another factor of 6, because I want to work in the integers and, instead of localizing. OK, and then let O, F, R be the set of points in the orbit for which f of v is an R almost prime. And the question is, when does that have this? When is this set? Maybe you'd like to think about this set as being finite or infinite. And I'll try to explain why that's not the right question. So let me show you a picture of this set. This is also in Alireza's talk. OK, can you see this? So here's the cone. That's better. So here's the whole cone. And some points are marked in blue, and some points are marked in orange. And at the very tip, some points are marked in black. So let me explain what that is. And then there are a bunch of points that are there but not marked, all these little dots. OK? So for which R, so the affine sieve question is, so the saturation number, definition, R0, given an orbit and a polynomial, is the smallest R, which could be infinite, so that the Zariski closure of this set O is the same as the Zariski closure of O itself. OK, so O is the set of all of these points, and the Zariski closure is just the whole cone. defined abstractly. It's just this cone. And we would like to understand the smallest r so that you still get the full Zariski closure. Why? Well, how many primes, so how often take on prime values? Or for how many primes do you need so that this function takes on infinitely many prime values? Looks like 2, right? It's a product of 2 things. So maybe it should be 2. Well, actually, this cone is isotropic. It has points on the cone over Q. It has rational points. Let's see. You can't see if I go over there. Let me come back here. It has rational points. And what that means is there are extramorphisms. There's a parametrization. There's a way of injecting affine space in. In this case, it's the classical parametrization. X is u squared minus v squared. Y is 2uv. Z is u squared plus v squared. That was known to the Babylonians 4,000 years ago. And so what does that mean? In these coordinates, f of v is x, y, x factors, y factors. There's a factor of 2 and a factor of 112, so there's a factor of 1/6. And for x, y, z to be primitive, u and v have to have opposite parity, so at least one of them is even. That kills off the 2. And u plus v and u minus v, one of them is a multiple of 3, so that explains all these local factors. Okay? So in fact, it should be a product of 4 prime factors infinitely often. But you can take special, so if we want all of the numbers to multiply to 2 primes, as was our initial guess here, 2, it's very easy to see that they're very, very highly restricted. You have the product of 4 things, most of which have to be 1s. Okay? So there's only a finite number of points, and those are the black points that you can't even see all the way at the tip of the cone. But what we could do is say v equals 2. And so now we're looking at the equation u plus 2, u minus 2 divided by 3, since one of these is going to be a multiple of 3. And then you would like to know, are there infinitely many, this is harder than the twin primes, are there infinitely many u so that u plus 2, and u minus 2 are simultaneously prime? And then you would get 3 prime factors. That's what these orange points are. These are the points where you get 3 prime factors. You could choose v equals 2 or negative 2 or 3 or negative 3 and get a similar result. This is the whole point of Zariski density, is we want to avoid, if we just say, if instead of Zariski closure we just said, what's the smallest r for which this set is infinite, then probably r equals 3 by these kinds of examples and standard Hardy-Littlewood type conjectures, probably r equals 3 suffices to make OFR infinite. But you're going to sit on this subvariety, which is generated, which is just the union of these lines. There's coordinate axes lines, essentially. So that's not filling out the whole cone. You're stuck in some subvariety. Okay? So the whole idea in Zariski density is you want to fill out the entire ambient space. And for that, you need 4 variables. And as Eli mentioned, as observed in Bourgain, Gambert, Sarnak, so the work of Green-Tau implies, in fact, in this case, R0 is 4. One of the very few times where you can pin down this saturation number. And that's very particular. It's because this linear form is a product of 4 linear forms in 2 variables. Okay, so it's a higher rank system. It's a system of finite complexity in their terminology to which you can apply this theory. Okay. And so here comes the word thin. So maybe this is example 4. Thin Pythagorean triples. All you do is, maybe just out of curiosity, for that reason the Apollonian example is much more natural, but it's basically the same thing 1 dimension higher. It's harder to see the picture of the 4 cone, the 3 cone sitting in 4 space. But what I'll do is instead of taking the entire group, I'll take some subgroup, let's say finitely generated subgroup, which has infinite index. And now again, I look at this cone, and let's see an example of that. So these pictures were in the earliest lectures of Peter's on this topic, before we knew about the affine sieve. And here's where thin naturally comes from. The number of points is much, much less. The directions in which these tentacles grow on the boundary are exactly the limit set of your group. The Hausdorff dimension of this set of limit points, if you projectivize, you get a set of limit points on the circle. That's the critical exponent of the group. And now what happened to the orange? These subvarieties, where 3 almost primes infinitely often, in the original setting, once you go to a thin group, there's no reason to still have those subvarieties. But you can't help but stay on the cone. And that's what the blue points are. So 4 almost primes remains, at least conjecturally, to be the saturation number, even in the thin setting. We can't prove it. So what can we prove? So for thin Pythagorean triples. So is this picture clear? Is this? You see what's happening, right? I don't know if you can see it all the way. But now it's just these technicals. The points aren't filling out the cone. And these special subvarieties that produced r equals 3 prime factors infinitely often aren't there.
Is this for a particular gamma?
Yes, the picture is for a particular gamma, yeah. You change the gamma, you change the picture. Yeah, absolutely. The nice thing about this example is it doesn't have any parabolics. So one way of recovering these subvarieties is to give yourself parabolics that live on these subvarieties. Okay, so this is something that, in fact, this was my thesis that Peter gave me. So starting all the way in 2007, and then with Hio, we continued studying these kinds of problems. We showed that so now you need a numerical spectral gap. Because if you actually want to write down a number r, it's going to come from whatever exponent distribution you had, and that, of course, needs to be made numerical. So this is using Gambert's thesis, which has a numerical gap in the thin case. So it started out at something like 40 instead of 4. It's a 4-dimensional sieve. Sorry. I'm doing the best I can. OK, very good. I should have said 4 gamma not too thin. Yes. What does not too thin mean? Thin, in these finitely generated examples, thin is equivalent to this Hausdorff dimension that came up in Hio's talk, the critical exponent of the group being strictly less than 1. And so now I want it to be thin. I'm allowing it to be strictly less than 1, but not by too much. I want maybe 0.99998 to be a lower bound for the dimension, so that you can write the best possible number. This is a general result, which works for any delta. But to write down an explicit number, we want to make the gap between the bottom eigenvalue and the next eigenvalue as large as possible. OK? So it started out at r equals 40. You can construct them explicitly. In fact, they were already constructed in Gambert's thesis. So I didn't see who asked that question. Yeah. How do you know they exist? So the existence of groups with large Hausdorff dimension? I think the question is, how do you know there exist groups with such a large Hausdorff dimension? Yeah. So in SL2Z, you can construct them. In SL2C, if you want Schottky groups with arbitrarily dimension close to 2, you're in trouble. So if that's what you're referencing, we're staying away from that. Exactly. If you, yeah, but if you want Uh-huh. So in this setting, examples are abundant. Yeah. So in the time remaining, what I'd like to do, okay, so let me finish this discussion. So it started out at 40. I'm just giving you the chronology. Then with Juzu Hong, we brought it down to 25. And then we didn't do it explicitly with Jean, but if you follow what we did, it brings it down to 19. And then most recently, my student, Max Ehrman, whittled it down to 18. So we're still a multiplier of 4 away, but it's getting closer and closer to. Okay, I don't know where the limit of this is. Probably this is the limit. It's a 4-dimensional. No. It uses advances in affine sieve theory, which is what I hope to talk about on Thursday. How do you? So let me give the method. Let me give the method that will get you this, and if you're a little not as naive as we were then, it gets you this.
Have you ever considered using a vector sieve?
We have, and it's been. Of course. Let's talk about it after. Yeah, yeah. It's definitely. We looked at it. Now it's been long enough that I don't remember what goes wrong. Or it doesn't get. Yeah, that's my next example. Is Peter and Liu. Okay, so let me give some indication on how to prove this, and hopefully I still have the key ingredient. So where are we going to get our level of distribution? So what's our sifting set? Sifting set, of course, is the values. We're trying to find R almost prime F, so it's the values of F on the orbit. Okay? So what would you like to do? You'd like to know how many points are there in a progression, which means how many vectors in the orbit of size. I'll tell you what the size is in a second, with the property that f of the vector is congruent to 0 mod q, right? It's divisible by q. Now, how big is the vector? We want these numbers to all be at most x, and the polynomial is quadratic in the entries, so I should take elements of size root x. So I'll take a ball of size root x in the orbit, cut the cone at size root x so that I get points of size x. Now, counting in the orbit poses its own particular difficulties, but let me ignore those for a second. In fact, that was the key in these works. These were the key ingredients, is how do you count in orbits. But in fact, you can pretend that you're not counting in orbits and just count in the group if you want to change the multiplicities a little bit. So what do you do? Well, a key ingredient. Okay, let me do two things at the same time. Let me change this slightly and say, well, what is the orbit? It's the set of gamma in your group gamma, and then the indicator of what's V, 3, 4, 5 triple acted on by gamma, and that's what you want to be congruent to 0 mod q. Now, this might have a stabilizer, and so you would need to mod out by a stabilizer, and of course you want to take in a ball, but now the ball might be skewed a little bit. And so the first thing you should understand is how many points are there in the ball, or perhaps how many points are there in the orbit, and how do these distribute? And so this is another place where the critical exponent enters. So the number of points, so just if I sum gamma and gamma in some ball, let me set this to be a free parameter t, just so that, so t in our examples root x, just 1. Well, I don't know what this is, and I certainly don't know what this is in higher rank, how to do these counting statements and how to do them effectively. But there always is some abscissa of convergence of this series. So this will be of size, so this will be no bigger than t to some delta plus epsilon, and it'll be big omega of t to a delta minus epsilon. Okay, so there's some number delta for which the group grows at that rate.
Different balls. So that one is in the
These are different balls.
but the same root x.
The same root x because the balls will be off by constants from each other. So this is not a true equality. I'll get back to that in a second. And so if there's some number t to the delta, which counts how many points there are, so how many points should there be in progressions? Here's the key step. If you get nothing else out of this lecture, which you might not, here's the key step for executing an affine sieve in the Archimedean setting. So let's take it from this point of view. I want to know how many elements are there in this ball with this property. And the point is f is a polynomial. And the polynomial mod q, we can factor through the group gamma q, the congruent subgroup. So let gamma q be the congruent subgroup. So this is the set of all elements, not in the ambient group. So this is not the standard definition. This is just in the subgroup, in this possibly a thin group, which are congruent to the identity mod q. Okay? And then you can write gamma as gamma q times the cosets of gamma q. So an element here I'll write as the product of, let's say, gamma 0 here times gamma 1 there. I'll factor it like this. And so what do we get here? It's a sum over these cosets, gamma 0 in the cosets, gamma q, and then a sum over gamma 1 in gamma q. So that's just this factorization exactly. And what properties do we need? We need gamma, which is the product of gamma 0, gamma 1, to be of norm at most x. Gamma 0, gamma 1 has norm at most root x, or t, let's say root x. And we need this property, the indicator function of this polynomial on gamma. Gamma, again, is gamma 0, 1, being congruent to 0 mod q. Okay? So what's the point of breaking it up this way? F is a polynomial. Gamma 1 lives in this congruence group, so mod q doesn't do anything. So this indicator function doesn't actually depend on gamma 1 at all. So this indicator function pulls back to here. It does depend on gamma 0, but it does not depend on gamma 1. And now all you need to know is how do you count in progressions in the group in Archimedean balls uniformly over cosets. That's where the spectral gap, the Archimedean spectral gap, comes in. And what you can prove in enough generality, certainly in the examples that I'm talking about, is, so let me write again, gamma 0 in this quotient, the indicator, this indicator function, f of v0 gamma 0, there is no gamma 1 anymore, is congruent to 0 mod q. And how many points should there be in this congruence group? Well, it should be the same as the number of points. Let me just write it as the number of points in the original group in the ball. But they should distribute. That's the distribute in these q progressions. And how many progressions are there? It's the size of the index, which is the number of cosets. And of course, there's an error. And the error, if you do this Archimedean, is it's this same thing to the power 1 minus theta, where theta is this spectral gap. This power savings exactly comes from the spectral gap property of the group. Now you add up however many cosets, you get some power of q here. That's the remainder term. And when you sum those remainders, you can sum them up to some power of x precisely because you have a spectrum. Okay? Doing this more carefully and not taking the full congruence group or some better congruence group gives you this. And if you want to get these results, then you start inputting bilinear forms techniques. Bilinear forms, dispersion, that all goes. But it's still, all of those techniques will go to improve a level of distribution, and then you apply a standard sieve, a weighted sieve. OK, I'm out of time, so let me stop there. Thank you.